Hello and welcome to another video on orbital mechanics. I'm still going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition, and I'm going through chapter 2 and I'm up to the point of doing parabolic trajectories. So I thought I would go through the theory on that before doing the questions that involve it. So I'll get on with it. The parabolic trajectory is just a trajectory. It's not an orbit. Where the spacecraft or object coming in has enough energy and therefore speed to come in and exit without getting captured into an orbit. Now, given any object coming into the vicinity of a body from outside the body, it's going to have enough energy to escape, because the energy coming in should be equal to the energy going out. Assuming there's no other masses getting involved, it should enter and exit without a problem. And when it's a parabolic trajectory, it's essentially just a mathematical kind of fluke. The eccentricity in this case is 1. And when it is 1, we can take advantage of a lot of simplifications. And so I'll go into those now. So we have the original equation for essentially any orbit's radius, and that's the angular momentum per unit mass squared over the gravitational constant times 1 over 1 plus the eccentricity times cos theta. So if you just put E equals to 1, it's a very basic simplification, we just get this. So this is probably the one you would use the most. And we also can say that if theta equals 0, then the radius is just h squared over 2, the gravitational constant, because this would be 1, so it would be 1 over 2. And then if theta equals 90, it would just be h squared over the gravitational constant, which I've called 2p. So I've labeled this p and this 2p because p is a periapsis, and then so I've made this 2p. In the book, this is half p, and this is half p, and this is p, but I didn't like that because this is the periapsis, so I'm going to call this 2p. So a point is coming in, it's the fastest point here, and then it goes out and slows down. And once it gets off into the infinite distance, when theta equals, well, essentially once this gets to -1, r will be infinite, so that's cos of 180. So essentially keeps going this way, and eventually this angle, once it gets far enough, is approaching 180. And that'll be an infinite distance. And at an infinite distance, the speed will be 0 relative to this point. But it would never get to the infinite distance, so that probably wouldn't happen. So the energy of a parabolic trajectory is 0. And we know that from this equation, because here you put E equal to 1, you get 0. And therefore, this equation that we have for energy is also 0. This comes from the equations for any orbit or trajectory. So we can rearrange that, and we will get the velocity, escape velocity, equal to the square root of 2 times the gravitational constant divided by the radius. Now it's the escape velocity because every velocity on this is an escape velocity. So at any point on this trajectory, it is at its escape velocity. So if you were on a circular velocity, your circular velocity would be the square root of the gravitational constant over the radius. And if you wanted to move to an escape velocity, you would need to be root 2 times your circular velocity. We're just going to do that by replacing this value over here and rearranging a little bit. And then you have the flight path angle here, and that is defined, as we've seen before, as E sine theta, eccentricity sine theta divided by 1 plus eccentricity cos theta, and E becomes 1, which becomes this, and then a simplification of this is to use the half angle rules, so that becomes 2 sine theta over 2, cos theta over 2, and this becomes 2 cos squared theta over 2. look those up on any trigonometry identity page. It should be clear what's happening here, and these cancel nicely. This squared cancels this one, and sine over cos becomes tan, and the twos cancel. You get tan theta over 2. And so when you remove the tans here, you just get the flight path angle equals theta over 2. So no matter where you are on this orbit, the flight path angle is always your true anomaly over 2. Then going on to the Cartesian form for that. So here we have this line here is r cos theta. I know theta is on this side, but this is negative and this is positive. So this ends up as a r cos theta of let's say 135 would be negative. Right, so that's fine. And then r sine theta up here. And we know r can be, we can say r is this. And we're going to replace this with the term 2p for simplicity. So if we take this 2p and put it here, right, and that becomes our r, then we can say x equals 2p cos theta over 1 plus cos theta. And that's just substitution of this and this and this. And then the y is the same, y equals 2p sine theta over 1 plus cos theta. And now in the book, they are using a slightly different value for p, but let's just stick with what I've done because I prefer it. They square both sides here. This is just a trick to reduce down the equation into and remove the theta from it. So you square both sides. So x over p, that's just rearranging, plus y squared over 4p squared. So that's just rearranging those bits there. Equals 2 cos theta, 1 plus cos theta. So that's that bit from the x, and this is the bit from the y, sine squared theta divided by 1 plus cos theta all squared. Now the top bit here becomes 1 minus cos squared theta, and then when you add those fractions together, you'll see the top line equals the bottom line, which equals 1. It's just a quadratic equation on the top when you add those together, and that quadratic equation simplifies to 1 plus cos theta all squared, so you get 1. So x over p plus y squared over 4p squared equals 1. And you can rearrange that, the x equals p minus y squared over 4p, or y equals square root of 4p upon p minus x. And just a reminder here that p equals h squared over 2 gravitational constant. And this is nicer than the one in the book. It's just a difference of a 2 there, but this one is nice here because y is clearly 0 when x equals p. So when x is p, it's here, and so y is clearly 0. And when y is 2p, which is here, right, x is clearly 0 again because 2p all squared is 4p squared divided by 4p is p, so p minus p is 0. So these look nice, right? So that's it, I think. I don't think there's anything else to do with parabolic trajectories. It's not very difficult because you're just essentially using the e equals 1 everywhere and simplifying. I do realize I didn't do the Cartesian system in the elliptical orbit video, so I might go back and do one of those. Otherwise, thank you very much. If you have any questions or comments, please leave them below. Thanks, bye.